See, when you take a program, so just to recall lecture 1, what happens when you take a program hello.c or whatever? So this hello.c, it is present in the hard disk. It is present in the hard disk of the program. And then we compile this program, gcc hello.c, and then a.out file gets generated, and this is also present on the hard disk. And then you give this a.out for execution slash a.out. This dot means you are giving the path of the executable file. So that you are telling, that a.out program that I am asking you to execute is present in the current directory. That's what it means. So what happens is when you give this thing for execution, so a main memory layout. So this is your CPU. This is your CPU, and this is your RAM. This is your RAM or main memory. Oh, it's not visible, huh? Yes, I am writing. Okay. I see what's the problem is. Your screen sharing is possible. Resume share. How about now? Can you see the writing? Okay. It looks like I messed up something. I understood the problem. Okay. Needs to be out of maybe. Okay. So you're all seeing, right? You're able to see, I hope. Great. So nice. So what happens is a main memory layout for the program. The instructions of the a.out which is present in the hard disk. Okay, the a.out that is present in the hard disk, it is loaded into the RAM. And so the main memory layout for the program is created. A main memory layout for the program is created. And so the logical, this is what you are seeing here is the logical view of the main memory layout of the program. Okay. So yeah, so you can see there is a part of the program of the main memory layout where the instructions associated with the program are stored. Like, for example, your the assembly language, the equivalent instructions for your functions that you write in your C program, they will be stored. C, we should not make unreasonable requests. So one of the requests that I got a private message is, sir, can you repeat once more? I got disconnected due to network issue. So many of you know with network problems coming, joining in, leaving all those things happen. If I keep repeating, no, we'll go nowhere. It's an unfair request, right? So please, no, when you are asking something, please think what you are asking for. Yeah, so Vaibhav, of course, no, like your C program hello.c, when in the binary form, it looks like hello.s, and hello.s contains instructions like add, subtract, branch, and but of course, this is not processor doesn't understand. There is an encoding for each of these instructions, like 1001, 0001. Oh, some encoding will be there. So this is what gets loaded in this code section of the program. And yeah, that is a binary file itself. It's true. The binary file itself contains the instructions in the binary format. And the data segment will be present, and then the data segment global memory for global variables, static local variables are allocated. If you look at the binary file tells the loader how to construct this data segment when it is given for execution. Like for example, if you have a global variable number of names, the memory, there is no main memory allocated in a.out for number of names, but there is an information in the a.out file. A.out file also contains a data section, and the data section contains information about different variables and the memory that needs to be allocated to these different variables when the program is given for execution. So if you think about it, your a.out, it contains, it's the recipe for it contains a recipe for the program execution. And when you give the program for execution, that recipe is put in for action. And then of course there is stack, and then stack is also where memory for local variables is allocated. And then there is heap, where memory for memory, whenever you do malloc calls, memory is allocated from the heap. There will be some other sections also, but these are the important things that you have to keep in mind. This is the logical view of your main memory, of the main memory layout of the program. Are you all with me here? Okay. So now if we keep going, so this is on a, if you see, this is a kind of a more detailed layout of the program. And so here, remember, let's say if you have 4 GB RAM, and for the time being, we can assume that the entire 4 GB RAM is available for your program for execution. The entire, your 8 GB RAM, the entire 8 GB RAM is available for your program for execution. Okay. So you can see this is the main memory. Your main memory, it has no, it starts, it has an address 0, address 1, address 2, so on and so forth. So if you look at your whole memory, some amount of memory needs to be allocated for the operating system routines. So this is the what is called as kernel virtual memory. Are you with me? Because part of the memories should be allocated for the operating system. So yeah, so part of the main memory layout, in part of the main memory layout, the code associated, the data structures associated with the operating system are stored. Are you with me here? Because and this particular layout that you are seeing, this is specific to say an operating system and a processor. If it is Windows operating system and some processor, the layout could be slightly different, but the logical sections will still be present. Yes or no? Are you with me here? First checkpoint. Want to see? The second point you can see, this is the place where your BIOS routines will be present. Some your bootloader and things will be present. So when you switch on your system, the instructions of the bootloader will start executing your grub or whatever, and then they load the operating system for execution. And this is usually for this we use either read-only memory or flash memory, because even when power supply is removed, the instructions and the data that is present there will still be there. They will not be lost. So in the rest of the memory layout, your program is present. So you can see there is a read-only segment. This is the place where the constants .ro means read-only data. .text means this is the place where your program instructions are present. And the read-write segment, this is the place where your global variables are present. And this is the heap and stack, they grow in opposite direction. This is the place where your local variables are allocated memory. And this is the place for global variables. It's not denoted. Macros, they don't have any memory. No memory. Macros are all replaced, right? So go check again. We saw that. It's convention. We can draw either ways. It's not like Vibo. It's having the address. It's not even a convention. It depends. You can draw both ways. And yeah. All right. And then in between, there will be some shared libraries, memory for shared libraries will be allocated. And this will usually be read-only. You will not be able to modify. So like, for example, when you write a program with some problem, recursive program with some problem in the base case of the recursion, and if it goes on infinite recursion, this stack keeps on growing. And finally, it can try to override the shared library region in which we can get a segmentation fault. Or it can go and overwrite the memory that is associated with the heap, and again, it can get into problem. So when you try to, when you write recursive code and when there are problems in the base cases, the stack keeps growing and it kind of overwrites, tries to overwrite other regions. And if we get into trouble, we get segmentation fault and the program crashes. No memory is allocated during compile time. The instructions for how to allocate memory during execution is what is present. BRK for the time being ignore. It is, I have to check once, but it roughly, it indicates some logical section of your memory. Okay. So good question, but I'm not sure right now. I have to check on it. So for the time being, just take this one, and then Janie, you have some good questions. I don't have answers. I need to check answers to those questions. These are details. But dot data and dot BSS, if you look at your assembly code hello.s, it contain, you will learn in your computer systems organization course a bit about these things. There will be a data section, there will be a text section. Here there will be instructions of your program here. Any memory for global variables will be allocated here, but this is all in the hard disk. This is like the recipe. But when you give this for execution, then the loader looks at the data section of your executable, and then it appropriately sets up the data section in the memory. And it looks at the text section of your executable, and it appropriately sets up the the text section or instruction segment of your memory. Okay, think of this as this is a recipe, and this recipe is used to create a main memory layout of your program. Are you all with me? Kind of. And one interesting thing though is, if you look at your program, if you look at your computer, there are many processes running on your computer, right? So how is it possible that these processes can use the same memory? Right? Because there are, if you see, if you use PS command or top, you will see so many processes running. And so yeah, so what happens is the memory that you're seeing here is not the physical memory layout. It is what is called as a virtual memory layout. What you are seeing here, that's the reason you see that virtual address space layout of a Linux process. This is the virtual address space layout, but not a physical layout. You will learn more about this in detail in your operating systems course. Yeah, but nevertheless, it's this is an interesting time to check on this once. So again, this is another picture, same virtual address space layout of a Linux process. You can see again here, there is a text segment, that is the instructions of the program are present in the text segment, and in the data segment, global variables are present. And BSS segment is the place where uninitialized variables, which are supposed to be filled with zeros, they will be present in the BSS segment. So don't worry so much about the distinction between data and BSS segment. Just think of them as alike. And then there is this heap, and then there is a stack. And I want you to pay particular attention to this random stack offset. So whenever you execute the program, the base address of the stack, it gets slightly randomized in order to counter what is called as a buffer overflow attack. There's a very interesting attack called as buffer over. I will share some information on this. There is what is called as a buffer overflow attack. In order to counter that, the base address of the stack is slightly randomized. So because of that, if you print the address of local variables in your program, every time you execute the program, the local variable address will be slightly changing from one execution to another execution. But most of the time, the global variable address remains the same. So this is to counter what is called as a buffer overflow attack. All right. So now, how this virtual memory gets mapped to physical memory. So like, for example, this could be your Chrome process. This is the virtual memory address layout of your Chrome process. And this could be the virtual memory layout of some video player, or let's say, or your own program video player. So this is the virtual address space layout of the Chrome process. This is the virtual address layout of the video player. So your whole virtual address space is, so this is virtual memory is a logical memory. So this is divided into pages, and so a page of Chrome, like for example, here, if you see, there could be multiple pages here. This segment is of Chrome. It can span over multiple pages, and they are allocated memory in this in the different physical pages. So similarly, you can see, like for example, in the video player, so there is part of the virtual memory, it got allocated. This part of the virtual memory is allocated memory in this part of the physical memory, and this part of the virtual memory is allocated in this memory. So when you look at the physical pages, some pages correspond to the Chrome process, some pages correspond to the video player process. Similarly, if you look at your whole memory, right now, if there are 100 processes running on your system, some of the physical pages in the memory, they could be belonging to one process that is running in the system, and some other set of pages could be belonging to some other set of processes running in the system. No. So the interesting thing is the BIOS here and here, all these things, they map to the same physical page. Even the kernel here, you see, the kernel here that is present, these all gets mapped to the same physical pages. So there is no wastage of space. So there is what is called as a page table data structure, which maps virtual memory pages to physical pages. You can think of it like a pointer to some extent. Virtual is not really there. Physical means it is there. Virtual is in our mind. So physically, you cannot go and actually find this page. Okay, like for example, this part of the memory in your virtual address space, it could be some hole, because like for example, the programs that you are writing, it's very small, so they hardly require any memory. So for so a lot of your virtual address space, it contains holes, means there is nothing really present there. So there is no physical memory allocated for those holes. Only when we start using those holes, then only the physical memory is allocated for those corresponding virtual memory pages. Okay. Yeah. Yeah. So I think so. Now I will switch to. Yeah. Let me switch to the core, our usual thing. So let's take a program. Is there a possibility of physical memory being written by multiple virtual memories? No, Shreya, because the operating system does the mapping. So if a physical memory is allocated to a virtual page of some process, it will not be allocated again to some other process. It's not possible. Just out of a curiosity question, is there anyone who is coding using VA editor? NeoVim, huh? Okay. Is it good, NeoVim? Okay. Code blocks. Okay. Code blocks is, I think it's good only. Yeah. Okay, so now, so let's look at, actually, let's see if there are any programs that we can use from before. What's the big deal? We will just, so hash include, so tell me one small program with, we'll use a global variable. Let's say, oh, I didn't share the screen. Okay. So now we will, so let's say we use a global variable int float pi is equal to 3.14 mean, and then ask the question float radius printf enter the radius scanf %f millimeter. Okay. Main, this return main is haunting us through the semester. Enter the radius. Okay. I have to use /n. Oh, sorry. Something. So this is what we have. So if you see where is scope extend.c is present, scope extend.c is present in the hard disk. Okay, a.out is also present in the hard disk. So GCC minus capital S scope extend.c. So now come here. So it generates an assembly code. If you look at the this, you can see here the data section in this assembly code, where it is being told that pi, there is a global variable called as pi, and it needs to be allocated memory in the data section of the main memory when this program is given for execution, and it has to be initialized using some value. This dot size tells how much of memory should be allocated to pi when we actually give program pi for execution. Are you with me? Data section in this program extends from line 4 to line 9. Line 4 to line 9. So this is the recipe. So when you give this program for execution, so allocate 4 bytes of memory for pi, and it has to be initialized with this 3.14 whatever value. but it is showing something, but the equivalent floating point number will be that. That's what I'm guessing. Okay. And then so we are talking about string literals, right? If you see the constants in this program, string literals, string constants in this program, we are using 3 string constants. Enter the radius, %f, perimeter, three string constants. They are allocated memory in what is called as a read-only section of the program. They are allocated memory in the read-only section of the program. So again, this when you give this program for execution, the memory for these strings are allocated in the read-only data section of the program. You can see this picture, right? So here, this is the read-only section. RO, this is read-only section. Okay. So this one gets mapped to, this is the recipe, because there's no memory allocated, they get. But when this program is given for execution, this recipe is followed to create this virtual memory layout. And this data section, this goes to this part. So pi is present here. All the string literals are present here. All right. So now when we go to, and this is the text section starts from line number 17. This is the place where the instructions of the program are present. This is the place where instructions of the program are present. Finally written. So all these instructions, they will be loaded into the text section of this program. So this is how it is done. And the interesting thing is you don't see a stack allocation, explicit memory allocation for stack. So there is nothing like explicit memory allocation for the stack. When this program is given for execution, the ESP register, what is called as a stack pointer register, it points to the top of the stack. And so that's it. So you just use the stack, push things onto the stack, pop things from the stack, from the stack, so on and so forth. And malloc also you don't handle directly, because malloc is handled by the memory associated with malloc, that is heap. It is handled by the malloc library. So you don't here manage this memory for malloc. Okay. But there is a very why we are studying all this thing is memory that is allocated in the data section, it lasts throughout the program lifetime. So I want to introduce you to this important idea in this class, which is called as a scope and lifetime of a variable. Scope and lifetime. The lifetime of a global variable is the whole program execution time. That is the pi variable, the memory for pi is allocated, it is there throughout the program execution time. But if it is a local variable, okay, so if local variables are allocated on the stack, so they are allocated memory only when that function is activated. So the lifetime of a local variable corresponds to the lifetime of the function activation, whereas the lifetime of a global variable is the whole program execution time. Are you all with me here? This is the very, very important point. Like for example, here, if you have something like float area, let's say you take something like float radius, compute area. So float area is equal to pi times radius. Return area. Okay. So if you see the lifetime of the variable area, it's not when you give the program for execution, at least in this program, since we are not invoking compute area at all, so it will never be allocated memory at all. It will be allocated memory only when we give, when we call compute area, then the memory for area will be allocated on the program stack. And when we are out of compute area, then it is, yeah, so then again it is deallocated. So the lifetime of a global variable is the whole program execution time. And how is it being achieved? Because it is allocated memory in the data section of the program. Whereas the lifetime of local variables in a function, it is only when the program is instantiated or activated. And after we are out of that function activation, then the memory allocated is released. Even that's the same thing true for main also. As long as main is active, then only the memory for radius is allocated. Main is just like any other function. It is only special in the sense we start from main. Are you all with me on the lifetime? Very important idea, very, very important idea. So you may see sometimes, let's say, you want to use what is called as a static local variables. Static int count. Let's say you want to figure out how many times that compute area function is called. Okay, let's say we are calling this for int I is equal to 1, I less than 10, plus I, compute area I, intf area of a circle of radius percent d is percent f I comma computing. Okay. So now if you compile this program, let's see, /n, thank you. And I would like to comment out this code, this perimeter code for the time being. Yeah. So you call this program 4 times with different radiuses, and we are printing. So let's say there are many cases where you want to keep track of some state information within a program. Let's say you want to know how many times compute area is called. Compute area function called for percent d times count. Okay, so now let's compile this program and sorry. So you can see that the value of the variable compute of the count, it is maintained across program invocations. So when we declare a variable as static, then the memory for when we come back to this compute area function, the previous value is still restored. Are you with me here? And so given that, do you think it is possible to allocate memory for count on the stack? Count is a local variable, right? Can we allocate memory for count on the stack? Yeah, if you allocate memory for count on the stack, it would be popped. So we cannot allocate memory for count on the stack. So we have to allocate memory for count on some other place. Let's see what it is. This change, or I should. What is this program name? Scope. Global compute area count. I'm just trying to see where memory for count is allocated. Move count. Yeah, so he did some trick, but in order to do some stuff, the compiler did some tricks. But the point here is count will be allocated memory somewhere in the data section of the program, because we want to retain what is the lifetime of the count variable. What is the lifetime of the count variable? Static local, this variable count, what is its lifetime? Throughout the program. So even when you exit the compute area function and when we come back, it is still there. It is still there. It is the program time. So the lifetime of a global variable. So just to summarize, we could have even used count as a global variable. No, so we will come to that. Good question, Vansh. Yeah, I recall. So in this picture, no, local variables are allocated memory. Static local variables are allocated memory in the BSS segment. Both are equivalent. Yes, so count will be stored like a global variable. That's true, Harsh. Yeah. So now, to summarize this whole discussion, what is the lifetime of a global variable? First question, what is the lifetime of a global variable? Program execution time. What is the lifetime of a local variable? Throughout the function activation time, function run, function execution time. What is the lifetime of a static local variable? It's program execution time. Excellent. So you all understood a fundamental important thing. This is the lifetime of a variable. Lifetime. When it is born, when it dies. Okay. So the next idea is the scope. What is the scope of a global variable? Scope is all the places where we can use that variable. What is the scope of variable pi? It can be used anywhere after its declaration. It's the whole program. The scope of this global variable is the whole program. What is the scope of the local variable area? Inside the function. Okay. What is the scope of the local static int local variable count? Inside the function. So a very interesting property of the static int count is its lifetime is throughout. Lifetime is throughout, but the scope is within that function. Scope is within that function, but the lifetime is the whole program execution time. So scope, inside function, lifetime, program, whole program execution time. There is static global variable. So we will come to that. So actually what static in the context of global variable, it means different. So let's do one thing. So are you all with me or here? So few things you may have to, there are few small things you may have to keep in mind. So like for example, let's say here, if I declare pi control X, control V, let's compile this program and see what happens. See, it says pi is an undeclared variable. That is the scope of a global variable starts from the moment it is declared. Okay, it's not visible before pi is not visible before line 70. But usually we declare global variables. Declaring global variables in the middle of a big program is a very bad practice. We should avoid that. Okay. Similarly, is the case here. Like for example, if you see within function also, like the scope of a variable is only after its declaration. The scope of a variable is after its declaration. Like for example, here float radius, if it is present here, then radius is available for use after line number 34. You cannot use but within the function, but after line number 34. All right. And what is the scope of the variable I here? Line number 30. What is the scope of the variable I? It is within the for loop. I is not visible outside the for loop. So in today's class, you learned two important ideas. One is called as a scope and other is called as a lifetime. These are the two important ideas that you learned in today's class. And I took a bit of a detour from our discussion from the last section, from the last discussion. We were looking at, now to conclude discussion on this, what is the lifetime of a memory that is allocated through malloc function? What is the lifetime of a variable that is allocated through malloc function? Until we free it, yeah, until we free we can use, but after we free it is gone. And is there any scope for a memory that is allocated through malloc? No, there is no scope. You can pass that address to anyone in the program and you can just use that memory. There is no scope. As long as you have the address, you can use it anywhere. So there is this question about global variables being static. I will take up that question in the next class, where we study about multi-file programs. That global static variables, they come into picture when we talk about multi-file programs. Okay. So we will, so we will revisit this idea. I want to clarify this scope lifetime, which is a fundamental concept, because so in the next class, What do you want me to do? You want me to continue with the linked list discussion, or you want to look at multi-file programs, or? Okay, then. So we will do linked lists in using multiple files. So everyone will be happy. So yeah, that's the plan for next class. Okay, guys. So that's all for today. And so I would say the ideas that you learned in today's class